So I've drawn out these 4 scenarios here. And what we want to talk about is what type of reaction is likely to happen in each of these scenarios. And if there is some type of reaction, how fast is it likely to occur? So let's look at this first scenario up here. I have an iodide anion, which we saw in the last video is a very strong nucleophile. So this right here is very, very strong nucleophile. And actually, we have the iodide anion in every one of these scenarios. So in every one of these scenarios, we have this very strong nucleophile. And let's see the other reagent that it might react with. Here I have a methyl carbon that's attached to a fluorine, or if we actually name this actual molecule, this would be what? This would be fluoromethane, just because we only have 1 carbon there. But when I say it's a methyl carbon, that means that this carbon is only attached to other hydrogens. It's CH3. It's not attached to any other carbons. Let me label all of them right now. So in this scenario right here, I have a methyl carbon. It's a methyl carbon, not attached to any other carbons. It is attached to this fluorine, and if we kind of pattern match based on other things, maybe fluorine is our leaving group. But what's left over, the substrate, we have this methyl carbon in the middle of it. Over here, this would be a primary carbon. It is only attached to 1 other carbon. So this is a primary carbon. It's attached to 1 other carbon. This one right here is secondary. It's attached to 2 other carbons. It's a secondary carbon. And then finally, this is a tertiary carbon. It's attached to 1, 2, 3 other carbons. So that right there is tertiary. So we've already identified the difference between the scenarios. All of them have this very strong nucleophile. And then the reagent, the thing that it might react with, the carbon in the middle has different levels of, I guess you could say, connectivity to other carbons. This has no connectivity. This is connected to 1 other carbon, 2 other carbons, 3 other carbons. So what's likely to happen here? Well, strong nucleophile. And let's say I'm not going to go too much into the solution just yet. I'll do a future video on that, probably the next one. But we have a strong nucleophile. Let's just say this is a good solution for doing SN2 reactions. And so there's no reason why an SN2 reaction can't occur here. Strong nucleophile, it can give its extra, let's say it's giving that electron right there. It could give its extra electron to the carbon, to this methyl carbon. And right as it's doing it, this fluorine could take away the electron from carbon, could take away that electron. So that electron could go to fluorine. So what I've just drawn here is an SN2 reaction. Once again, S stands for substitution, N stands for nucleophile, and then the 2 means that both of the reagents are active in, this really is only 1 step of the process, but in the slowest part of the process. And this is the slowest part of the process. This is actually the whole process right here. So we get an SN1 reaction. We get SN1 reaction going on. So we have a substitution with a SN2 reaction. I want to be very careful here. SN2 reaction. We have substitution with a nucleophile, and both reactants are present during the rate determining step. And there's only 1 step here. So both of these are involved. Now let's think about what happens in this scenario over here on the right. What's going to happen over here? Well, once again, strong nucleophile. It's not too different. Now this is a primary carbon. We have a little CH3 group over here. But this thing should still be able to get its way into that carbon. It still should be able to give its electron. It still should be able to give its electron to that carbon. And then this electron that the carbon had could now go to the fluorine to make a fluoride anion. And I haven't drawn the final step, but you've seen SN2 reactions before. But once again, this is an SN2 reaction. SN2. Now, we said not only what would happen, but we also said how fast might it happen, or how can we compare them. I'll tell you right now that this one on the left is going to happen very fast. Very fast, relative to this one, which will only happen fast. I'm not giving any absolute numbers, but we're just comparing them relatively. And the reason why this is very fast and this is only fast is because this one has this CH3 group in the way. So this is a big part of a molecule. This is big. This right here is big, especially relative to just a hydrogen atom. So this is big. This allows less directions with which, remember, all of these chemical reactions in organic chemistry and chemistry in general, you always draw them as these nice organized things, but these are really just these atoms and molecules bumping into each other at just the right way with just the right energies. And if you have this big thing blocking kind of one of the entry paths onto the carbon, you're not going to have this reaction happen as quickly. There's going to be some times that maybe the iodide ion was coming from the direction and it gets deflected by this over here. In this case, it wouldn't have, because that hydrogen isn't big enough to deflect it. So this is going to happen just not as fast as this one right here when we're dealing with the methyl carbon. And I think you see where we're going here. So what happens when we have two of these carbons right over here? When we're dealing with a secondary carbon, a carbon attached to two. If the solution is right, and we're going to talk about the types of solutions that favor SN2 reactions, we will have an SN2 reaction still. We'll still have an SN2 reaction, but it will be slower than these guys up here. So we still are going to have an SN2 reaction, but it will be slower. It will be slower. So far, this is the fastest, this is the next fast, and this is slower than either of those two. And it's the same exact logic. This only had one CH3 blocking the entry into this primary carbon. This has two CH3s. It has this one over here. It has this one over here, and it has this one up here. So it lowers the likelihood that an iodide anion will be able to bump into this carbon in the exact right direction. So that's why it's going to occur slower. This iodide anion has to come in just the right direction for it to occur. That's less likely, so overall the reaction is slower. Now finally, what's going to happen here? Well, you might be tempted to say, well, this is just going to be really slow. But the reality is that this tertiary carbon is blocked really in every direction. It's really in every direction. It's blocked there, and blocked over there. So this iodine anion is actually not even going to be able to get to it. So I'll write no SN1. And we'll see in the next video that maybe there's another type of reaction that we've learned. Sorry, I should say SN2. No SN2. I'm sorry if part of my brain makes me think that I might have said SN1 or no. Everything in this video is SN2. Everything in this video, we have the nucleophile attacking the other reagent. They're both present, so it's SN2. Although my brain sometimes wants to say SN1. These are all SN2 reactions, and you're not going to have an SN2. And actually, if your solution is right, you actually might have an SN1 reaction here, and we'll talk about that later. But you have no SN2 here, because the nucleophile cannot get to the carbon. It's blocked by these, I guess we could say, these methyl groups. Now, the term for this blocking, I guess you could say, of the point that the thing needs to attack or kind of give its electron or move into is called steric hindrance. Steric hindrance. You know what it means to hinder something. It's you're making it hard for it to happen. And steric just means kind of three-dimensional, or the kind of the shape of the three-dimensional shape of things, hindrance. So by the virtue of the three-dimensional shape of this, or kind of the way that this is made up, it's blocking the reaction from happening. It's hindering the reaction. So the big takeaway from here is you're only going to have an SN2 reaction. You're going to have a very fast SN2 reaction if you're dealing with a methyl carbon. A little bit slower if you're dealing with a primary carbon. If you have a secondary carbon that's blocked by two other carbons, it might happen if the solution is just right, but it's going to happen very slowly. And if it's completely blocked, then you're going to have no reaction. And the one last thing, you might be saying, well, hey, how can I not come from the other side? You can't come from the other side because the point that you want to kind of give the electron that it's taking away is kind of being blocked by the fluorine in this situation. That SN2 reactions will only happen on the opposite side from the leaving group. Just as a reminder, this is the nucleophile, this is the leaving group. And SN2 reactions, the nucleophile goes from one end, and then the leaving group leaves from the other. It cannot happen on the same side, which actually makes a lot of sense if you think about it. That's as opposed to the SN1 reaction, where it can happen on the same side. And what we'll see is if the solution is right, this type, having a mixture of this and this, would actually favor SN1. I'll do a whole video on that, but you could think about what happens. If the solution is right, the fluorine can take this electron first, then this will become a carbocation, and this would actually be a very stable carbocation. The very same thing that was causing steric hindrance will actually make this a stable carbocation, and then that will make it favorable for a nucleophile, really even a weak nucleophile, to I guess attack it or to bond to it or to give it its electron.